Hello, welcome to another module in this massive open online course. So far we have seen several concepts in information theory. We have seen the definition of entropy, joint entropy. Let us look at yet another related quantity, which is the conditional entropy. Okay. So we will start looking at another important quantity in information theory, that is the conditional entropy. Entropy, as we already said, characterizes some measure of information, correct? It's conditional entropy. Okay. So let us say we have again two sources x and y. Okay, we have x and y. Then h of the conditional entropy, remember similar, so h of y conditioned on x, that is entropy of y conditioned on x equals, well, summation I equal to 0 to m minus 1 probability of x equal to Si times the entropy of y conditioned on x equal to Si, which is equal to, well, let us look at how these quantities are defined, which is equal to I equal to 0 to m minus 1 probability x equal to Si times summation j equal to 0, correct, j equal to 0 to n minus 1 probability of y equal to Rj conditioned on x equal to Si times log to the base 2 1 over probability, that is, this is the entropy of y given x equal to Si. So, we are using the conditional probabilities. Okay. So, this is the entropy of y conditioned on x equal to Si, this is the probability of x equal to Si. So, this is basically the entropy of y conditioned on the source of x, or entropy of y given x. Okay. Now, this can also be written as follows. So, this can, let me just simplify the notation a little bit. This is equal to I equal to 0 m minus 1 probability of Si times summation j equal to 0 to n minus 1 probability of Rj given Si times log to the base 2 1 over probability of Rj given Si. Now, if you take probability of Si inside and multiply this, take probability of Si into probability of Rj given Si, that is y equal to Rj given x equal to Si, that is simply probability of Si comma Rj. So, this will be summation I equal to 0 summation j equal to 0 to n minus 1 probability of Si into probability y equal to Rj given x equal to Si times log 1 by probability Rj given Si, and now this quantity is basically probability of Si comma Rj, that is x equal to Si and y equal to Rj. So, this is equal to sum I equal to 0 to m minus 1, sum j equal to 0 to n minus 1, probability Si comma Rj log to the base 2 1 over probability Rj given Si. This is the quantity conditional entropy of y given x. This is the conditional entropy of this is the entropy of y given x. So, this is the conditional entropy of So, this is basically the uncertainty in y, correct, the uncertainty in y given x, okay. Having observed x or having given the source x, what is the uncertainty in y, okay, what is the uncertainty in y, okay. So, this is the definition of conditional entropy. Now, let us look at an interesting property of this quantity conditional entropy. H of y given x plus h of x. I would like to look at what this quantity is. This quantity is summation. First I am going to write h of y given x. This is probability of Si comma Rj log 2 to the base 1 by probability Rj given Si okay. This is basically your h of y given x plus summation I equal to 0 to m minus 1 probability entropy of x. This we have seen several times before, probability of Si times log 2 to the base probability of Si summation over all I, okay. So, h y given x plus h of x. Now, look at this entropy of x I can also write as h of x. I can also write this as, remember probability of Si is nothing but probability of Si Rj summed over all j. So, I can also write this as, well, j equal to 0 n minus 1. I can also introduce a summation over all j equal to 0 to m minus 1 probability of Rj Si 1 over probability of Si, and therefore, h of y given x plus h of x, you can see this is basically summation I equal to 0 to m minus 1 summation j equal to 0 to n minus 1 probability Si comma Rj log 2 to the base 2 1 over probability Rj given Si plus summation I equal to 0 to m minus 1 summation j equal to 0 to n minus 1 probability Si comma Rj log to the 2 to the base 1 over probability of Si. And now if you add these two, now you can see I can take probability of Si Rj common. So, that will be summation I equal to 0 to m minus 1 summation j equal to 0 to n minus 1 probability Si comma Rj, and when you add the two logarithm the arguments multiply. So, this is log 2 1 over probability of Rj given Si into probability of Si, and now observe that probability of Rj given Si into probability of Si, this is equal to probability of nothing but Si comma Rj, that is intersection of Si comma Rj, and therefore, this is going to be, now you can observe this is summation I equal to 0 to m minus 1 summation j equal to 0 to n minus 1 j equal to 0 to n minus 1 probability Si comma Rj log 2 to the base 1 over probability Si comma Rj, and if you can recollect, this is nothing but the joint entropy of x comma y. Okay. So, the very interesting relation that we have here is that H y the conditional entropy of y conditioned on x, y given x plus h x is nothing but the joint entropy this is the conditional entropy h y given x plus h x equals h x. Similarly, you can also show naturally there is nothing special about x and y. So, if I reverse the roles of x and y, h x given y plus h x of y is also equal to h. So, this is another interesting property of this, is basically another way to express again. So, I have h y given x plus h x is equal to the joint entropy h x comma y, which is the same as h x given y plus h of y. And so, we have also seen h y given x is the conditional entropy. You can also see this is basically nothing but the uncertainty. Remember, entropy is the uncertainty. Okay, entropy is the uncertainty. So, conditional entropy is the uncertainty remaining in y. One can say, so you have conditional entropy. Entropy is nothing but the uncertainty. Remember, is the information conveyed by a source or is the uncertainty in a source. So, you can say the conditional entropy is the uncertainty remaining in y having observed x. Okay. So, this is h y given x equals uncertainty remaining, okay, the uncertainty remaining in y having observed x, and h x given y, and of course, this is the joint information in x and y, this information. So, uncertainty, so let us look at it this way, let us write it over here, uncertainty remaining in y given x, h of x is uncertainty in x, this is joint information or joint uncertainty in x and y. Joint uncertainty in x and y. So, we have uncertainty in x plus the uncertainty remaining in y given x, that is the joint information of x and y, joint entropy of x comma y. Okay. So, we have this interesting property. Let us look at a simple example to understand this better. Okay. alright. So, let us look at a simple example. Let us go back to our previous example that we had, where we had this table of probabilities. Okay, so this is what do you have? This is your S0, S1, S2, S3. This is your R0, R1, R2 at 3. The joint probabilities are 1 by 8, 1 by 16, 1 by 32, 1 by 32, 1 by 16, 1 by 8, 1 by 32, 1 by 32, 1 by 16, 1 by 16, 1 by 16, 1 by 16, 1 by 4. Okay. Now, each entry P of ij, remember, equals P of, well, x equal to Si, y equals Rj. For instance, this denotes P of 0 comma 3 equals P of x equals S0 comma y equals R3 equals 1 by 32. And from this we have computed the marginal probabilities of each S0. Probability of x equal to S0 is simply the sum of the probabilities in the corresponding row. That is, you sum the probabilities of S0 corresponding to each Rj, that is P of S0, Rj summation over j gives the probability of S0. That is, we know that by the total probability rule. Okay. So, that is, we have computed this before. So, probability of each S0, all S0s are equiprobable, probability is 1 by 4h, probability of R naught is half, R1 1 by 4, rest are 1 by 8, 1 by 8. Okay. Now, what we have to do is we have to compute, let us say, the joint probability. So, we want to compute the probability of well, y given x. Let us first start by computing probability of y given x equal to S0. For that, we will need the probability of y equals Rj given x equal to S0. Now, if you look at this, for instance, probability of y equal to S0 given x equal to S0 equals probability given x y equal to R1, let us say y equal to R1, y equal to R1 equals probability of S0 comma R1 divided by probability of S0 comma R1 S0 comma R1, for instance, that is 1 by 16 divided by 1 by 16 divided by probability of S0, probability of S0 is 1 by 4 equals 1 by 4. So, probability of, remember, we are using the simple principle that probability of A given B is probability of A intersection B divided by probability of B. Okay, we already know the various joint probabilities. For instance, if we want to compute probability of S0 Rj given x y equal to Rj given x equal to S0, that is simply equals probability of y equals Rj comma x equal to S0 given the probability that x equals S0. We already know these quantities. This is nothing but P0 comma j, that is probability of x equal to R0 comma y equal to Rj, and the probability of x0 we already know this probabilities, these are the marginal probabilities. Okay. So, we see, for instance, probability of y equal to r0 given x equal to r0, that is the probability of r0 s0, that is 1 by 8 divided the probability x equal to s0, that is 1 by 4. So, this is 1 by 8 divided by 1 by 4 equals, well, half. Similarly, probability y equals r1 given x equals s0, we already calculated that, that is basically 1 by 16 divided by 1 by 4 equals 1 by 4. Probability y equals r2 given x equal to s0 equals, well, 1 by 32 divided by 1 by 4, 1 by 8, which is also equal to the probability that y equal to r3 given x equal to s0. So, the entropy given entropy of y given x equal to s0 corresponds to entropy of a source with the 4 probabilities: probability y equal to r0 given x equal to s0, that is half, y equal to r1 given x equal to s0, that is 1 by 4, and the remaining probabilities, that is 1 by 8, 1 by 8, which is basically, again we can form the entropy of this source. This is basically half log to the base 2 1 over half, that is 2, 1 by 4 log to the base 2 4 plus 1 by 8 log to the base 2 8, and in fact there are two symbols with probability 1 by 8. So, into multiplied by 2. So, this is 1.75 bits. Okay. Similarly, one can calculate h of y. So, we have gone, so using the conditional probabilities of the various symbols y equal to r0, r1, r2, r3 conditioned on the fact that x equal to 0, we are able to calculate the conditional entropy of y given x equal to s0. Next, the conditional entropy of y given x equal to s1. Okay. This is equal to the entropy corresponding to the probabilities, well, 1 by 4, again the same, 1 by 4, 1 by 2, 1 by 8 comma 0, which is equal to 1.75. h of y given x equal to s2, this is equal to h of, this probabilities will be equal 1 by 4, 1 by 4, 1 by 4, 1 by 4, because if you look at given x equal to s2, all the symbols are j, the joint probability of all symbols is 1 by 16. Okay. So, each probability, that is y equal to y equal to rj given x equal to s2 will be 1 by 16 divided by 1 by 4, that is 1 by 4. So, the conditional probabilities will all be 1 by 4 in this case, and the joint the entropy will be, well, 1 by 4 log to the base 2 4 into, there are 4 symbols with probability 1 by 4. So, this is basically 2, and finally h of y given x equal to s3, this will be equal to h of, well, 1 0 0 0, because you can see in this case the joint probability of all symbols other than the symbol r0 are 0. So, their conditional probabilities will be 0, conditional probability of x equal to y equal to r1 r0 given x equal to s3 will be 1 by 4 divided by 1 by 4, that is equal to 1. Okay. So, that is an entropy of a source with probabilities 1 0 0, and this is basically certain, which means given x equal to s3, the only symbol y can take will be r0, because the rest all have 0 probability. So, there is no uncertainty, which means this conditional entropy given x equal to s3 will naturally be 0, and that you can get also from this calculation corresponding to the probabilities 1 0 0 0, and therefore, finally, we have h of y given x equals summation, well, I equal to 0 to m minus 1, m equal to 4 in this case, probability x equal to si into entropy h of y given x equal to Si, which is equal to, well, that is equal to 1, probability of x equal to S0 is 1 by 4 into entropy x given y given x equal to S0, that is 1.75, plus probability of x equal to S1 is 1 by 4 into entropy y given x equal to S1, that is 1.75, plus 1 by 4 probability of x equal to S2 entropy y given x equal to S2, which is equal to 2, plus 1 by 4 is probability x equal to S3 into entropy y given x equal to S3 is 0, and if you calculate this, you will get the answer. This is equal to 22 by 16 equals 11 by 8, which is equal to, well, this is equal 22 by 18, this is equal to 1.375. So, this is equal to 1.375. And now, if you remember, h of x equal to 2, we have derived, this is basically, this quantity is h of y given x. All the source symbols have, all the symbols of x have uniform probability 1 over 4. So, h of x equal to 2, we have calculated this, h of x equal to 2, this is equal to h of, because all the marginal probabilities are equal to 1 by 4, and you can check that h of x plus h of y given x is equal to 2 plus 1.375 equals 3.375, which is indeed equal to h of x given y. We had also computed h of x given y, which is now the joint entropy of x comma y. Okay. Similarly, you can also check that h of, well, y plus h of x given y should also be equal to h of x comma y. You can also check this. So, you can check this. Okay. So, basically that is what we have. We have seen the definition of conditional entropy. So, in this module, what we have seen is we have explored yet another concept, that is the conditional entropy. Okay. The conditional entropy of y given x and x given y, okay, which is the conditional entropy of y given x is the uncertainty remaining in y having observed x. Okay. So, we have h of x plus h of the important property that we have seen, h of y given x equals h of y. This is conditional entropy. Or information in y, uncertainty in y given x. This is the information in x. This is the joint information in x comma y. This is the joint information in x comma y. Alright. So, we have seen conditional entropy, its properties, and an example to illustrate how to compute the conditional entropy. Alright. So, we will stop here and continue with other aspects in the subsequent modules. Thank you very much.